Okay. Okay, student, the record button is now on. So I hope you are good to go there. Sit in the most comfortable way. So again, a very good morning to all of you. Selamat pagi semua. Yeah, Wang Beijing until 7.1. Okay, so for the exam, okay, before we start, before the exam, okay, the topics cover for Form 4 is all chapter from Form 1, from chapter 1 until chapter 6. Okay, and then for Form 5, chapter 1 to 3, chapter 1 until chapter 3 cover all, and then followed by chapter 4.1, 5.1, 5.2, 6.1, and 7.1. Okay, so please be alert with that. For Form 5, 1 to 3, all. Chapter 4, 4.1 only. Chapter 5, 5.1 and 5.2. And Chapter 6, 6.1 only, radioactive decay. And 7, 7.1 only. So are you clear with that, students? Beijing? Okay. So you note down all the remaining chapters. So today we are going to have 5.1 and 5.2 tomorrow. So we have another 2 to cover for your trial, 6.1 and 7.1. Okay, so this is chapter 5, electronics. Okay, so we are going to discuss the first content standard 5.1, electrons. Okay, it's a very short chapter, short topic, and you can find this in your textbook cover from page 174 until 180. Okay, that is the pages. Okay, students, before this, we have learned in chapter 3. You all have learned in chapter 3 that current is the rate of flow of charge. Okay, current is the rate of flow of charge. And we also have learned that an electric current is produced when charge or electron flow in a conductor. Okay, the question here, can electron move through a vacuum without a conductor? What do you think? Can electron move through a vacuum without any conductor? Okay, so the answer is can. This is what we are going to do in this content standard 5.1, electrons. Okay, so this is the three learning standard in 5.1. The first one, each and every one of you must know how to describe the ionic emission and cathode rays. Okay, what is the ionic emission? What is cathode rays? And second, to describe what is the effect of electric and magnetic field on cathode ray. Okay, what happened to the cathode ray in an electric field? What happened to the cathode ray in the magnetic field? And last but not least is to determine velocity of an electron in the cathode ray tube by applying some formula and calculation. So this is the page cover for this content standard 5.1 electrons, starting from page 174 and then at page 180. Okay, welcome for those who just being here. So we just started, nothing to worry. So let us begin with the first learning standard, students. So I want you to focus on this discussion. Okay, so nothing to write, but you can jot down a few notes, okay, in your notebooks or whatever. Okay, so this is the describe thermionic emission and cathode ray, our first learning standard, students. So what is thermionic emission? Okay, what is a thermionic emission? This is a process. Okay, it is a process. Anyone would like to give a try? What is thermionic emission? What is electron? Ong Jiang asked. Anybody would like to respond to that? What is an electron? Okay, you learn in chemistry. Where can you find electron? Emission of electron from metal surface under high temperature. Good try, Nicholas. Anybody else would like to say what is the ionic emission? Welcome, Zheng Yang. So students, as said by Nicholas, I would like the precise meaning. I would like the precise meaning for electron. Haha. So what is electron? Anybody can respond to Ong Zheng? Okay. Okay, so this is what meant by thermionic emission. Okay, don't ignore me. I didn't ignore you, Ongzeng. We carry on with our lesson first, can? Okay, so thermionic emission is the emission of free electron from a heated metal surface. Okay, So inside a metal, you've learned before, we have an atom. Okay, inside we have proton, electron, and neutron. Okay, proton, electron, and neutron. So thermionic emission is what? It is the emission of free electron. Okay, emission means the release of emission of free electron from a heated metal surface. It means that when the temperature of a metal is increases, they will start to release electron from the surface. Okay, later you will see in chapter 7, photoelectric effect. Okay, then we will see what is the difference between thermionic emission and photoelectric effect. Okay, students. Okay, then if you look at this short animation, okay, and I believe you all know that metal has free electron, okay. Any conductor or any metal has a free moving electron that move in a lattice structure as shown here, but it does not have sufficient energy to escape from the metal surface because they are bound to the strong nucleus attraction. Okay, so this is what happened under normal temperature. Okay, they have free electron, but they are just moving around the metal in this lattice structure as shown here because they have not enough, sufficient means not enough. Okay, they don't have enough energy to escape from the bonding, from the attraction force from the nucleus. All right. Okay, then what happened? Once the metal is heated, the temperature is increases, then this electron will acquire enough energy so they can escape from the metal surface. All right. So this is what happened when we are heating a metal surface. We call the process as a thermionic emission. Okay, thermal, something to do with heat. Is something to do with temperature change. Okay, next. Okay, so this is the factors affect rate of thermionic emission. Okay, factors affect rate of thermionic emission. There are 4 altogether. The first one is temperature of cathode. Can you guess how does temperature affect rate of thermionic emission? Anybody would like to give a try? Okay, so directly. So yes, when temperature increases, so the rate of thermionic emission increases. Mean the higher the temperature, more electron will be released, more electron will be emitted from the metal surface. Okay, then second factor is the surface area of cathode. Okay, what do you think the relation here? Surface area and rate of thermionic emission. So logically, it will also directly proportional. Okay, when the surface area increases, the rate of thermionic emission increases because a larger area, we have more electrons there inside the structure. Okay, then type of metal. So for the third factor, different type of metal has a different rate of thermionic emission. Okay, for example, tungsten, barium oxide, and strontium oxide has a higher rate of thermionic emission. Okay, then the fourth factor, specific heat capacity of the cathode. We learned before in Form 4, Chapter 4, specific heat capacity. What does it mean, student? Specific heat capacity. Anyone remember? Specific heat capacity. What does it mean?
Require to raise 1 degree Celsius of 1 kg metal.
Okay, so very good. Amount of heat required to increase the temperature of 1 kilogram object by 1 degree Celsius. So what do you think the relationship here, specific heat capacity and rate of thermionic emission?
Inversely proportional.
Inversely proportional. So it means that lower specific heat capacity metal will have a higher rate of thermionic emission. Remember, lower specific, they require small amount of heat only to increase the temperature. So they release electron in a shorter time. Okay. So again, temperature, surface area, type of metal, and specific heat capacity are the factors affect the rate of thermionic emission. The emission of electron from a heated metal surface. Okay, next student. Okay, what is cathode ray? So you understand the first one, thermionic emission. Second is cathode ray. So have you ever heard cathode ray? Cathode ray. Electron beam. Okay, yes. Okay, so cathode ray is a narrow beam. of fast moving electron in a vacuum. The keyword is the yellow word, fast moving electron. Okay, a group of electron which move in a high velocity in vacuum. Okay, that is cathode ray. A normal electron, we didn't call it a cathode ray. Only when they are moving at the highest speed in vacuum, then we call it that movement as cathode ray. Okay. So after electron has been released, just now we heated a metal surface. So then electron will be released. They will form a narrow beam of fast moving electron. Okay. So this cathode ray can be produced where? By using an electron gun. Have you ever heard electron gun, students? Electron gun. Where can you find these tools? Okay, electron gun, it is assembled in your television, for example, to produce the picture. Okay, if you notice, the ancient television is very big in size, very bulky, because the electron gun back there is very, very big. But now they make it smaller, and some television are not using electron gun anymore, so they are using another technology like LED TV, LCD, the liquid. Cikgu tak ingat apa nama dia. But LCD is using liquid inside. Okay, and this electron gun is what we call as a cathode ray tube. Okay, cathode ray tube. You boleh Google cathode ray tube atau electron gun. Okay, so you can see this is how the shape look like. Lebih kurang macam ini. It has one cylindrical cone there and the apparatus. So this is, you can see when we switch on this high voltage power supply, so the electron will be emitted from the cathode and accelerating to the anode, assembled in a straight line, and it can be displayed on this screen. Okay, so it appears as a green fluorescent color on the screen there. Okay, so again, what is cathode ray? A fast moving electron in a vacuum. Okay. Okay, next students. Okay, this is the structure, the basic structure of a typical cathode ray tube and how it works. So the parts is numbered with number 1, number 2, number 3, number 4, and number 5. So you can see the cathode is there at the back. Okay, so this is where the electron will be emitted from when we connected when we on the EHT power supply. Extra high tension power supply means a very high voltage power supply. It supplied 3 to 4 kilovolt. Okay, and this is another connection connected to the cathode. Okay, so when we on this, okay, this cathode will be started releasing electron, and this part is connected to the anode, so they will be attracted to the anode. Okay, and will be hitting the screen, and you will see the effect as a fluorescent color there. Okay, so number 1, how is this process occur? The first one, what happened at this part at the cathode? The cathode is heated by a tungsten filament. Okay, you can see a coil shape there, that is a tungsten filament. Okay, remember in chapter 3, tungsten is material we always use we normally use as a heating element. Okay, other than nichrome. Okay, then students, the heated cathode, then what happened? Okay, the heated cathode will emit electron, and this electron will be accelerated at high speed between the anode and cathode because a high voltage is applied between this anode and cathode. So here at the cathode, we apply normal voltage, example at 6 volt. But at the anode, it's applied with very high voltage. So it creates a big potential difference. Okay, it creates a big electric potential difference. So the electron will be accelerating, attracted to the anode since it is negative charge, right? So they will be attracted to the positive anode at a very high speed. Okay, then what happened at number 3? The vacuum glass tube is used to prevent collision of electron with air molecules. So inside this tube is vacuum. Okay, it doesn't fill with any kind of gas because we want to prevent the collision between the electron and the air molecule. Say they will moving in a straight line here. Okay, so no disturbance inside the tube. Okay, then the accelerated fine beam electrons strike the fluorescent screen and causes the screen to become green in color. So this is the effect that you are going to see. Then finally, the beam of electron is what we call as a cathode ray. So this is the process occur inside the cathode ray tube, starting from how the cathode is heated until finally you see a green fluorescent color on the screen, showing that cathode ray is produced. Okay, are you clear with this process, students? What happened inside the cathode ray tube?
Yes.
Okay, then we take a look at the next part. Okay, this is what happened inside the tube. Okay, the motion. Okay, so this is the structure you are given. P there. P is our cathode. And what is Q, student? What is Q? Q is our anode. Okay, anode. You can see cathode is connected to the negative terminal. Okay, and the anode is connected to the positive terminal of the extra high tension, high voltage power supply. Okay, so what happened here? The cathode ray are produced by creating high potential difference between the cathode and anode by using EHD as I mentioned just now. Okay, then what happened? The negatively charged electron are drawn towards the positively charged anode with a high velocity. So when we switch on the power supply here, the filament, tungsten filament will started to hit the cathode. Okay, so at a certain rate, then the electron will started to emit. Okay, in this direction. Okay, first they are emit in a various direction. Then only they will be enter a small hole here at the anode. Then they will be assembled moving in one line, and this is their final destination at R. Okay, the screen. So what do you think the type of motion in this region from P to Q? Okay, what do you say? What can you say about the motion of the cathode ray from P to Q? How they are moving? They are moving in uniform acceleration. Okay, uniform acceleration means the velocity is increasing uniformly. Okay, then once they reach Q, so from Q to R, what do you think happened to the motion? Here they will be assembled in one line. So now they are moving at uniform velocity. Okay, uniform velocity heading to the screen. So at PQ, the movement is uniform acceleration, and from Q to R, they are moving in uniform velocity. Okay, so later we can calculate how fast they are moving. What is the maximum velocity they can reach? Okay, so that is to do with our first learning standard. You must know how to write thermionic emission. It is a process. And second is what is cathode ray. Okay, there are two definitions in learning standard 1. Okay, now we move to the second learning standard to describe the effect of electrical field and magnetical field on cathode ray. What happened to the cathode ray, student, when we place them in between electric field and magnetic field? So what do you think will happen? What will happen to the cathode ray? Okay, so first and foremost, you must understand first, these are the characteristic of cathode ray, students. Okay, cathode ray is a negatively charged particle, negatively charged. It has a negative charge. Second, they travel in a straight line in vacuum. Okay, as you see before, the short animation before in the previous slide, travel in a straight line in vacuum. And then they travel at high velocity, high kinetic energy, and high momentum. Okay, number 4, they produce fluorescent effect on the screen of the cathode ray tube. Okay, and number 5, they will be deflected. They will show deflection in both electric field and magnetic field. So where they are going to deflect to, this is what we are going to discuss in this second learning standard. Okay, so to investigate the characteristics. So these are the two apparatus we can use to study the deflection of cathode ray in electric field and in magnetic field. The first one is called as a Maltese cross tube. Okay, if you look at the vacuum inside, we have a cross there. This is what we call as a Maltese cross. Okay, another one is called as a deflection tube. So we insert a deflection plate, okay, inside the tube. So you can see the difference between these two structure. On the left, multi cross tube. On the right is deflection tube. Okay, so this is all another structure. Is about the same. The cathode, anode, okay, the EHT, and this is the normal power supply. But this is the effect for both. Okay, and here for deflection tube, we add another EHT power supply here, connected to both positive plate and negative plate on top of the deflection plate. All right. Okay, so what will be the find out? So as I mentioned, we can study the characteristic of the cathode ray by applying these two apparatus. Okay, so when we are using multi-cross tube, this is what we can find. Student number one, we can see that cathode ray travels in a straight line, okay, in this cathode ray tube. Second, they are deflected by magnetic field, okay, and they produce fluorescent effect on the screen. Meanwhile, for the deflection tube, this is the come up from the finding. Okay, the first one, the cathode ray is deflected. It shows deflection in electric field. And second, it is proven that cathode ray is negatively charged. Okay, so how to see? Okay, this is actually you can find also in your textbook. We take a look first, the cathode ray which is placed in between an electric field. Okay, so this is the deflection plate. As you can see, the positive plate is on top and the negative plate is before. So we have three switches there, students. Okay, this is the first switch S1. Second switch is connected to the EHT. The first switch S1 connected to the 6-volt power supply. And another switch here S3 is connected to the high voltage power supply connected to the deflection plate. Okay, so this one, the first EHT connected in between the anode and cathode. Okay, so what happened when S1 and S2 are switched on? S1 and S2, we close. We close S1 and S2. So what happened? You will see that no electric field between the two metal plates. Okay, so why no electric field? Because this one is not switched on. Okay, this one is not switched on. So what happened here, the cathode ray will be emitted from the cathode, accelerating towards the anode and continuously travel in a straight line until it reach the screen. Okay, this one. So we prove here cathode ray travel in a straight line. Okay, now what happened? We turn on all switches. S1, S2, S3 are all switched on. Okay, which means now we switch on the deflection plate here. So what do you think happened, students? So the cathode ray will start to show deflection, okay, as shown here. When you place positive above, so since cathode ray is a negatively charged, so it will be attracted to the positive plate. So it will deflect upwards, okay? And when you reverse the plate, place negative on top and put the positive plate below as shown in the diagram in the right side here. So now the cathode ray will be deflected downwards again towards the positive plate, okay, because it is negatively charged. So here we prove cathode ray are negatively charged. Okay, before that, when you on S3, the electric field is exists between these two plates. So when cathode ray pass through the field, it will be attracted to the positive plate terminal. Okay, very simple, right? To understand. So here we have proof cathode ray are negatively charged and it will be deflected to the positive charge terminal when placed in an electric field. Okay, are you clear with this, students? For activity A, to discover the deflection of cathode ray in the electric field. Okay. Okay, next. Now we want to check the deflection of cathode ray in magnetic field. What will happen to the cathode ray once we place them in a magnetic field? Actually, it is similar to what you learned before in 4.1. What happened to the conductor? What happened to the coil when we place them in between a magnetic field? So they will show a force. Okay, a force is acting on them, so they will move in a certain direction. So this one is also the same. So force acting, so it will show deflection to a certain direction, where we can determine the direction by using Fleming's left hand rule. Okay, so this is the relation between 4.1 and this chapter in the deflection of cathode ray in a magnetic field. Okay, so this is Maltese cross tube. Kalau dia tanya dalam objective, they give you this diagram. So you know this is Maltese cross tube. If they put a deflection plate there, so you know that is deflection tube. Okay, so the first condition, we have two switches here. S1 is connected to the 6-volt power supply, and we have S2 down there connected to the EHT power supply. Okay, now we turn on S1 only. So turn on S1. So what happened? So the cathode ray will be, okay, you see what happened here. The light from the hot tungsten filament is blocked by an opaque object. Okay, this cross is made from an opaque material. Opaque mean, what is meant by opaque? I mean light cannot pass through. It's not transparent. Okay, light cannot pass through, so it will cause a shadow to be formed. Okay, so here. So you will see this shape, only a shadow, no fluorescent green color, student, when only S1 is switched on. So it means that light travels in a straight line. Okay, my question, student, when we switch on S1 only, is there any cathode ray release from the cathode? Is there? If I switch on S1 only, is there any cathode ray release from the cathode? Yes or no? Yes or no? Ada atau tak ada?
Yes.
Ada atau tak ada? Actually, yes, ada. Okay, but what happened? Since this one is not on, so they are not accelerating towards the A naught. Okay, so they are moving around this area only, the cathode ray. So that's why here you only see a shadow formed from the light of the tungsten filament. Okay, there is no cathode ray reaching this screen. Okay, so here we prove light travel in a straight line. When you block, so you'll see a shadow is formed. Okay, a shadow of the blocker. Okay, then what happened next, students? So now we on both switches. S1 and S2 are turned on. So the EHT is now turned on, mean the anode is turned on. Again, when S1 is turned on, the film tungsten filament will be heated, so it heat up the cathode. Cathode ray will be released, so now they can accelerate to the anode. Okay, since this one EHT is on, so they will accelerate at the A naught. So here they assemble as a narrow beam of light. Then they will touch this Maltese cross tube again. So what will happen then? So this electron, they will move at the edge. They will move at the edge of the Maltese cross. So now you will see that they will be appear as a fluorescent green screen here on the screen, as shown in this short animation. Okay, so here cathode ray are blocked by the Maltese cross to form a shadow, and at the same time this cathode ray produce a fluorescent effect on the screen surrounding the shadow. Okay, okay, dia punya screen ini fluorescent screen. So dia ada cathode ray, and then you display to the screen, so it appear as a green color. Green color shows that cathode ray is reaching. Cathode ray is reaching the screen. Itu maksud dia, turn green. Because of the fluorescent screen. Kita pakai fluorescent screen. Okay, and then once it detect cathode ray, so you can see the effect. It will be have a luminous effect on the fluorescent screen. So here we understand again cathode ray travel in a straight line, and when they are travel at a high speed, they also have a high momentum and high kinetic energy. Why is fluorescent? So we can see the effect, Nicholas. Okay, bukan screen yang biasa lah, so we can see the effect. Then only you will prove, okay, cathode ray is produced inside this fuse. Okay, inside this tube. Yes, to be more obvious. Okay, Okay, then students. Okay, now again S1 and S2 are turned on, switch on. And now we bring a magnet closer to the tube. Okay, for example, as seen in this diagram on the left and on the right. So you will see now the shadow will be deflected from the center. It deflects to a certain direction. Okay, as shown here. Okay, so one shadow is due to the light from the hot tungsten filament. Okay, can you see here we have double shadow there? Okay, the shadow at the center is due to the shadow from the light emitted from the tungsten filament. Another shadow will be shifted. Okay, so here it will form two shadow. Another shadow will be shifted to a certain new location due to the deflection of the cathode ray by the bar magnet placed near to the tube. And how to determine the direction of the second shadow? We can determine, as I mentioned, using Fleming's left hand rule. Okay, for example, shows up here, this is our cathode ray, okay, which is emitted from the cathode. Okay, so they are traveling to the front, which means current flow in the opposite direction, students. So remember, current and electron are flowing in the opposite direction. We learned this before in chapter 3. So for example, when you place your finger, our cathode ray is always travel to the front, okay, from the cathode ray, which means that our current, okay, our current is always flow into, okay, opposite direction as shown here. Okay, the current flow into. Okay, and then second, you have to determine where is the polarity of the magnetic field, which is bring closer. Okay, for the first diagram, okay, this dot showing that the magnetic field is out of the paper, which means you bring north. Okay, you bring north to the tube. Mean S is at the other side. So here we say magnetic field is out of the paper. So the force will be upward. The second shadow will be shifted upward. Okay, and in the second condition, again, this is how our cathode ray move to the front, shown by the red line. And this is our current, always opposite direction to the movement of cathode. And here X mark showing that the magnetic field is into the paper, which means we bring south. Okay, we bring south closer to the deflection tube. So at this moment, the second shadow will be shifted in a downward direction, okay, according to Fleming's left hand rule. Okay, nanti kita cuba buat latihan and you try to see where is the direction of the second shadow move to. Okay, so are you clear with this? This is example lah shown by this man. He bring a magnet with a north polarity towards the tube. So you can see that the cathode ray shifted, okay, upwards. It deflected in the upward direction, follow his procedure. Okay, this one out mean N, bring closer. This one into the paper means south, bring closer to the tube. Okay, any question on this? Explain the polarity of the magnet again. Okay, this one, you bring north closer. Okay, you bring north. Okay, this one north closer. So the magnetic field will be out of the paper because it means the magnetic field pointing to the south. Okay, pointing to the south. So north closer mean south pole is at the other end. So we understand magnetic field is out of the paper. Yes. Okay, this one. Then second, when you bring south pole closer. Okay, let's say this is south pole closer. So now the magnetic field is into the tube. So what happened? It is deflected downwards. Okay, can? Yeah, near the tube. So kita sama macam near the paper lah, the tube ini. Okay, in and out. Okay. Okay, then that is the effect of the deflection of cathode ray in electric field and in magnetic field. I think for the electric field, no problem, right? Very obvious. It will somehow deflect to the positive terminal. Only for the magnetic field, you have to look carefully. where is the flow of current. That is actually simple, but the one that always confuse you will be the direction of the magnetic field. So you have to check. If you bring North Pole closer, so mean magnetic field is out of paper. If you bring South Pole closer, mean the magnetic field is into the paper. Then you place your finger in the correct position. You will determine either the second cross shifted upward, downward to the left or to the right. Okay. Okay, then this is the third learning standard to determine velocity and electron in a cathode ray tube. Okay, just now we say they will travel in a very high speed. Okay, so electron that release have an electrical potential energy due to the high potential difference here. Okay, so once they are travel, they will convert electrical potential energy to kinetic energy. Okay, so here they have electric potential energy, and once they are released, electric potential energy convert to kinetic energy. Okay, move to the screen. And finally, when the electron hit the screen, the kinetic energy convert to light energy. So energy changes occur for two times. First, electrical potential energy convert to kinetic energy, and then kinetic energy convert to light energy. So here what happened? The electrical potential energy is given by this formula. E ini number charge of one electron, and V ini is the potential difference. Okay, and then for electrical kinetic energy is half mv squared. Okay, as you learn in chapter 2, kinetic energy half mv squared, which mean here EP equal to EK. Okay, equal to EV equal to half mv squared. So this is the relationship between potential energy and kinetic energy. Okay, then okay, this is the equation. Electrical potential energy, sometimes they put P there, sometimes with no P. So it is equal to EV. So what is E, student? Electrical potential energy. What is E? Charge. Okay, charge of an electron. We learned before in chapter 3. This is the charge for one electron. 1.6 times 10 negative 19 coulomb. And capital V ini apa? This is the potential difference between the cathode and the anode from the EHT supply voltage. Okay, so E equal EV. Okay, then what next? So this is the relationship between electrical potential energy and maximum kinetic energy. As I mentioned just now, EP equal EK. Okay, electric potential energy equal to the kinetic energy of the cathode ray. Okay, so we write back EP equal to EV, EK equal to half mv squared. Okay, so by this we can find the maximum velocity. It is given by 2 EV divide m square root. Okay, square root of 2 EV divide m. What is E again? Charge for one electron. V, capital V, is potential difference between cathode and anode. M is mass for an electron. This is the mass for electron. It is a fixed number. Similar to this is a fixed one. So V max, okay, the maximum velocity of it. So you have to be careful here because we have two V there. Potential difference is capital V. Velocity is small v, this one. Okay, this V is velocity, and a capital V on the right side, this one is potential difference. So there are two V there, so you don't get confused. Capital V, potential difference. Small v, velocity. Okay, so you can jot down this formula. Velocity is given by square root of 2 EV divide m. Okay, so that's it. Learning standard 1, learning standard 2, learning standard 3. Student, simple, very short, right? Okay, we try a few example of question. Okay, so which particle escape from the surface of a metal when it is heated at high temperature? So which one is escaping? Okay, so we try to answer these exercises. Okay, so yes, answer is electron. Okay, electron. Then second student, question number 2. Okay, this is the diagram shows the vacuum tube used to investigate the ionic emission. Okay, what is the function of cathode, student? So where is cathode? This is cathode. What is the function of this cathode? Is it A, is it B, is it C, or is it D? So the answer is A. Okay, to produce electron when it is heated by the tungsten filament. Okay, how about B? Who did this work to accelerate the electron at the high speed? Okay, this is done by the anode. Okay, accelerating anode. And C, to control the intensity of the electron beam, this is done also by the anode. Okay, to deflect the electron beam vertically, this is done by the Y plate anode. Actually, we have a few anodes, so this all done by the anode. A is done by the cathode. Okay. Okay, then students. Okay, next. Okay, which particle is cathode ray? Okay, which particle is cathode ray? Cathode ray is actually an electron beam travel in a high speed in vacuum. Okay, so answer is A. Okay. Okay, then next question number 4. Okay, this diagram shows the process of electron escaping from the surface. Okay, so we apply heat here. It gains sufficient energy so it can escape from the nucleus attraction force. Okay, so what is the process? The ionic emission. Okay, what about the rest? Are you following me? Only Nicholas responding here. Okay, okay, then number 5, student. Number 5. Okay, this is a Maltese cross tube which we can use to study deflection of cathode ray in a magnetic field. Okay, what is observed when S1 is open? Okay, S1 is open. This is S1, mean only S1 is open. So what will you observe here? Okay, is it A, no glow on the fluorescent screen, or B, the cathode ray move with lower velocity, or C, the cathode ray move with higher velocity, or D, the shadow of Maltese cross becomes clearer? Okay, which one? Okay, just try on Jung. Okay, no problem. Okay, which one? S1 only open. So when S1 only open, what happens, student? As I mentioned before in our table, so S1 open, S2 is not open, mean there is no electrical potential here. So the cathode is released, but they will hanging at this area only because they doesn't reach the anode, so they doesn't reach the screen. So you'll see the shadow form due to the light coming from the tungsten only, so there is no glow on the fluorescent screen. Yeah, no green. Okay, only light from tungsten, black shadow. Okay, then next. Okay, again we have a Maltese cross tube. Now same situation, but now only S2 is open. Okay. What can we observe when S2 is open? Okay, betul lah soalan ini. Okay, what is observed when S2 is open? The first question tadi S1 is open. Okay. Actually this one close. Salah ni soalan dia ni. Okay. So now we close both. S1 and S2 is both close. Soalan ni sedikit salah lah. Okay. Close. Which mean light do not bend when magnet is placed near. Light is not bend when magnet is placed near. Which one? Light does not bend, only electron. The electron is bending. Okay? The electron, because it is charges. Okay? Only the electron bending. Okay, not the light itself. Okay? So which one? How to answer number 6, students? Okay, what happened? There is no green light appear on the fluorescent screen. Betul kan ni? Ni open. S2. Soalan dia sama kot. Sorry, soalan ni silap sikit. Okay. So I think question 5 and question 6, right, there is no green light appear on the fluorescent screen. Ini you abaikanlah soalan ini. I think question ini, yeah, only S2 is open. Betul lah, only S2 is open. S2 is closed. Ini sepatutnya close. This one is, which means this one is closed. So this, this is open, so S2 is closed. So there's no green light appear on the fluorescent screen. Okay. Sebab sini dia sebenarnya soalan ni salah ni. Actually S2 close. Okay, this one close. Mean this one only close, so S1 open, right? So if S1 is not connected, mean there is no cathode ray appear. So only the cathode and anode only. So no, there is no cathode ray exist here. Okay, it could be this. So there is no green light appear on the fluorescent screen. There is no glow. So this question is quite confusing. Tak apalah, you abaikan. Okay, but we understand that in order to form a fluorescent screen here, you must close both. S1 close, S2 also close. S1 close, so we can produce cathode ray. Cathode ray can be emitted from the cathode surface. And then S2 is open, so it create high potential difference. So now the cathode ray can accelerate to the anode and then can accelerate to the front. So they will be blocked by the Lemaste's cross tube. So you'll see a fluorescent green effect around the shadow. Okay. Okay, next. Okay, question 7, student. Okay, this is how to apply Fleming's left hand. Okay, you are given again Maltese cross tube. Okay, now we place 2 magnet bar at this position. North is placed on top and south is placed at the bottom, which means that your index finger will be pointing downwards. Okay, pointing to the south. And then this is the direction of the cathode ray, which means current is flow in the opposite direction. Okay, so you see the middle finger pointing into, okay, in this direction, index finger pointing downwards. So now you can see where is your thumb pointing at. It is pointing where? Pointing to A, pointing to B, pointing to C, or pointing to D. A is upward, B downward, B and D is to side. This one to the right, D is to the left. So the answer is yes, it will be deflect to the left. So the shadow, the second shadow will be deflect to the left side. Sini you akan nampak ada satu Maltese cross shadow, the second shadow. The first shadow remain at the center, shadow from the light from the tungsten filament. Second shadow is deflected due to FBI Fleming's left hand rule. Okay, how to see? Tengok ini, tengok di bawah ini. Okay, see the position of magnet. So index finger pointing downwards. Okay, as seen here. Then current opposite to the motion of cathode ray. So current move in this direction. Current. Okay, and then your force will be pointing to the left side. Okay, yes, N to S. N to S. Only one bar magnet. One bar magnet, kalau one bar magnet, okay, macam tadi kan. Okay, kalau dia put one bar magnet, let's say this one. Okay, this one N. Another side itu S. Okay. Okay, this is the tube. Okay, this is the tube. Okay, they bring north closer. So which means current magnetic field out or in. So your index finger pointing where? Pointing to the south. So this one magnetic field is out. Okay. And if you bring S, okay, if you bring S, magnet bar, mean this side is north. So now your index finger pointing into, okay, into. Okay, so I hope you are clear with that for those who asking. Okay, now we try to calculate, student, using the formula I showed you earlier. Okay, it shows an electron from cathode being accelerated towards the anode. Okay, so the electron moving from the cathode to the anode. So the potential difference between the two plates is given 750 volt. Okay, this is the potential difference. Find the speed of electron that strikes the anode. Okay, what is the speed when the electron reach the anode? You are given with the mass of electron. So this is M and this is the charge, okay, for one electron, which is E. So this is capital V. So we have M, we have E, we have capital V. What are we finding here? Speed, small v. Okay, can you find them using this equation? Okay, I give you a few seconds to find what is the velocity or the speed of the electron when it strikes on the A naught. Okay, everyone, please work on this. Okay, Nicholas, get C 1.62 times 7 power, 10 power of 7. Do you agree with him? Hisian, Zilin, Ong Zheng, Wanjia, Yujie, Wei Jing, Yuan Han. Please work with this equation. Okay, and what is the speed of the electron when they strike on the A naught? So you write the formula. This is the substitution. Okay, make sure you substitute correctly. 2, this is E given 1.6 times 10 negative 19. And this is the potential difference, 750 volt. M is the mass of electron, 9.11 times 10 negative 31. So it will give you, yes, 1.623 times 10 to the power of 7 meter second. Okay, 1.62 times 10 power of 7 meter second. Okay, last question for today. Okay, this is taken from your textbook, example number 1. Okay, figure 5.5. Oh, where is the figure? I forgot to place the figure. Okay, cikgu tunjuk you dia punya figure lah sekejap. Okay, you can check from your textbook. But I don't remember. This is on page 180. 180. 180. Okay, I check to you the figure first. Okay, so what is this is the information you are given. Okay, mass of electron 9.11 times 10 negative 3, negative 31, charge of electron 1.6 times 10 negative 19, and this is the potential difference across the A naught and cathode, 550 volt. Okay, this is the missing diagram. Okay, I cut for the diagram first, then can paste it there. Okay, this one. Okay. Okay, there is our missing diagram. Cikgu letak dia di sini lah. Okay. Okay, students. Okay, so this is the diagram. Shows the beam from the cathode accelerating to the anode. So the first question, what is the electrical potential energy of an electron, student? What is the electrical potential energy of an electron? Okay, how to find electrical potential energy? I showed to you the formula earlier. E equal to EV. Okay, electric potential energy, E equal to EV. Okay, so this one. Okay, E equal EV. So this is the charge, E 1.6 times 10 negative 19, and V is the potential difference, 550. So the electric potential energy is 8.8 times 10 negative 17 joule. Okay, this one. The formula is E equal EV. Okay, question B. Can you tell me what is the kinetic energy of an electron when it reaches the A naught? Okay, so here it leaves cathode with a potential electrical energy of 8.8 times 10 negative 17 joule. Okay, so when it reaches the A naught, what is the kinetic energy, students? Perlu kira ke, B? Do you need to calculate kinetic energy? Need to calculate or don't need? Tak perlu. No need. Okay, what is the relation of the electric potential energy and the kinetic energy? Are they the same? Are they equal or different? Okay, just now we say electrical energy convert to kinetic energy and then convert to light energy, right? And students, due to principle of conservation of energy, so the energy remain, only the form changes. Only the type of energy changes, but the magnitude remain. Yes, Wanja, equal. So B, you have nothing to calculate. So applying principle of conservation of energy, as I mentioned just now, the kinetic energy gained by an electron equal to the potential electrical potential energy of the electron. So A and B answer is the same. 8.8 times 10 negative 17. Then later, finally, what is the amount of light energy produced when they reach the screen? What is the amount of light energy produced when they hit the screen, when the electron beam, when the cathode ray reach the screen? Same also, 8.8 times 10 negative 17 joule. Okay, we ignoring any energy lost, okay, due to principle of conservation of energy. Even though in the real life, there will be some energy loss somehow. But when we are doing our calculation, again, we understand that, okay, we take into concern, we apply principle of conservation of energy. 100% electrical potential energy convert to kinetic energy, and then 100% kinetic energy convert into light energy. Okay, final question C. What is the maximum velocity of the electron when it reach the A naught, student? So how to find the maximum velocity? So we apply the previous formula as in question 8. Okay, so this is the maximum kinetic energy equal to the potential electrical energy. Okay, electrical potential energy. So half mv squared equal to EV. So you just bring this to the other side. So we are looking for this maximum velocity equal to square root of 2 EV divide M. Again, you do the substitution. So this is E. Okay. And then E is missing there. Where is EV tadi sudah kira kan this one. So this one is EV. Okay, we already calculated here. So we put 8.8 times 10 negative 17, and this is the mass, 9.1 times 10 negative 3. Okay, so the answer is 1.39 times 10 power of 7 meter per second. So this is the maximum velocity the cathode ray reach, okay, when it hit the A naught. Okay, so any further question? Okay, can you follow me for 5.1? Students, anything you would like to ask regarding this chapter from what we have discussed starting from 8:36 until now 9:35 a.m. Ada apa nak tanya? Okay. Okay, so this chapter is quite short. Okay, so you only have to understand what is the ionic emission, what is cathode ray, and how is the process occur inside the cathode ray tube, starting from we turn on the switch connected to the filament. So the filament heat up, it will heat up the cathode will emit electron. So this electron will accelerating to this A naught, and this electron is called as cathode ray. Okay, and finally you will see a fluorescent effect on the screen telling us that they are moving in a straight line in vacuum. And then second, we have checked what is the deflection effect when we place cathode ray in between an electric field and in between a magnetic field. And last but not least, how to apply the equation to find the potential, electrical potential energy, Vmax, okay, and so on using that formula. Okay. Again, any question? Okay, I think I will end up the recording first. Okay, so later you can check back from the recorded video if needed. Okay.